Surf's up. It's spring break here on Question Field. Welcome back, everyone. I am Brian, and I'm joined as always by
Campbell.
And today's a special episode for two reasons. The first reason is, Campbell, we have our first listener submitted question.
Extremely exciting stuff.
Extremely exciting. And there's another reason this episode is so special, and it is because we are joined by our first guest.
Hello.
That's right. Yeah, we've got James here, James Moore, who is also a PhD student at Cambridge with me. So we, have had many a lunch break spent in the same place.
Very nice.
So yeah, welcome, James. Thanks for joining us on the podcast.
Yeah, thank you.
Thanks for having me. Thanks.
No worries.
Yeah, just to give everybody an idea of what this has taken to pull together, it is currently 6:40 in the morning for me here in New York. Campbell, it's
20 to 9 p.m. For me in Sydney. I'm currently here on a bit of a holiday, and then James is in the UK. So what's it?
11:40 a.m. for me. So,
right.
So it's a perfectly reasonable time,
Nice.
really. So.
Oh yeah, we had to work around the guest here.
Yeah. Glad it's working for you, James.
Thank you. Thanks.
No, seriously. Thank you for being here. Yeah. Exciting stuff.
James, maybe you could just tell us a little bit about who you are and what you're doing in your PhD and that kind of thing.
Sure. Okay. So I'm James Moore. I'm a PhD student at Cambridge, as Campbell already mentioned. So I'm finally a PhD student now. So I've been at Cambridge quite a long time now. And I specifically work in particle physics, specifically working on proton structure with Dr. Maria Ubiali. We work mainly on the interplay between proton structure and the discovery of new physics. So new particles beyond the standard model, and we see, is there room inside protons for new physics, basically? So to make it sound as sexy as possible, but the day-to-day reality is more to do with fitting and kind of statistics and this kind of thing. So yeah.
That was a great intro to what you do. Thanks, James. And you also did your undergrad at Cambridge, right?
Yeah, that's right. Yeah.
And you're also staying there after your PhD for your first postdoc. Is that correct?
That's right. So it'll be a long time at Cambridge. So so part of the furniture, but yeah.
A very tried and true Cambridgian.
But yeah.
James, let me ask you real quick, because Campbell was completely unfazed by this, but we talked on a previous podcast about how Newton's tree got uprooted, and he didn't care at all, was the impression I got. Of course, you must have been horrified and devistated.
Oh, I don't think so, not particularly. So I don't know. So I think I am also fairly unfazed by it. So I think I'd only seen the tree a couple of times, to be honest. I don't know. Yeah. So but yeah, and calling it Newton's tree is perhaps generous. I don't know. Maybe it's a bit apocryphal, perhaps. I don't know. Yeah.
This is what I said exactly.
Perfect.
Yeah.
So we were contacted by Andrew. So thank you, Andrew, for writing in.
Yes, thank you.
So Andrew has asked us about a fairly broad question. He says that he's a mechanical and manufacturing engineer, and he said that one thing that's mesmerized him is resolution of measurement error calculations in general, and was interested in how these things fit into the theoretical side of physics. So this sort of reading this email, I thought it was a very interesting question, but one that I didn't feel very qualified to answer myself, because I don't deal with measurements at all or data at all in my PhD. But it got me thinking about a conversation that James and I had a little while ago on the research topics that he works on, and specifically on how you calculate errors in particle physics and how you sort of propagate these errors through your calculations, and the kind of difficulty associated with quantifying like how good these methods are, and and really how successful they are in general. So that's kind of the question for today, I think, is we'll talk through a bit more about what James's research is, maybe a bit about what we know about proton structure and what there is left to find out. And I guess, broadly around this theme of how do we quantify how good the knowledge is that we have about particle physics? So yeah, maybe we can just dive into some intro to the proton. So what is it that you're actually trying to study about these things, James?
Oh, yeah, that's a great question. Yeah. The proton is kind of a super interesting particle in particle physics at the moment, because it's the central object of study at the LHC, so the Large Hadron Collider. The Large Hadron Collider smashes together protons, beams of protons, and it measures what comes out when we do the collision. So we see lots of junk comes out, and we detect it, and we infer some things about the collision as a result of the stuff that we see. But protons themselves are quite complicated objects. They're quite difficult to get hold of in terms of the theory, because they are not elementary particles. They are composite particles that are composed of smaller particles that we think are elementary particles. In particular, they're composed of quarks. So you may have heard that they're composed of 2 up quarks and a down quark, but this is not the whole story. So a proton is not just a collection of it's not a bag containing these 3 particles. It really is kind of more like a bubbling soup of particles, where there's lots of virtual exchanges between these quarks, these 2 ups and these downs. Perhaps a more accurate statement is to say that on average the proton is really 2 ups and 2 downs, and there's actually this virtual soup that's going on at the same time. One of the biggest constituents in this kind of virtual soup is gluons in particular, which are kind of the glue holding together the proton, and they account for about 50% of the proton structure a lot of the time. So yeah, but there's also lots of other particles that can appear as well. So there's strange quarks, charm quarks, or lots of antimatter that can appear in the proton as well, in much smaller quantities, but it can be important. And so when we fire 2 protons at one another, it's important to understand the structure of the proton, where in terms of predicting what kind of results we're going to be getting out. And modelling that structure is complicated, as you can imagine, because of the huge amount of interactions that are going on inside, the huge virtual stuff inside.
It was very frustrating that quantum mechanics doesn't give us this nice. It doesn't sort of obey this nice picture that we have of it.
Exactly.
2 ups and a down. Yeah.
It would be very nice if it was just some billiard balls being fired at one another, and But to an extent, though, we can. This is when we actually do make predictions. We kind of, to an extent, try to stay close to the classical picture as much as possible, and try to add on the kind of quantum corrections. So when we actually do make predictions in terms of firing a proton at another proton, the standard way of generating predictions is originally due to Feynman, actually. So in terms of the model that is used, and it's something called the parton model for the proton. And what we do in the parton model is we assume that the proton is traveling really, really quickly. So it's traveling very, very close to the speed of light, which is roughly true for colliders. So the protons move very, very quickly. So we fire them at one another, and as a result of kind of special relativistic effects, we have this time dilation effect for the proton. So viewed from the reference frame of the other proton, we have this time dilation. And on the kind of scales that are appropriate for this time dilation, it looks like the interactions inside the proton have to take place over a very long time as we approach the collision. So in fact, you can approximate at the moment of collision that the interactions between the constituents of the proton are happening very slowly. So you can imagine that perhaps they're not actually interacting very much. You can treat them essentially as billiard balls at the moment of collision.
So these are the quarks and the gluons as well that are
also the gluons as well. So so unfortunately you do have to treat all of the constituents as well fairly. But so the ups and the downs, but also the gluons and also the other constituents. And you can imagine that at the moment of collision, there's actually just one constituent perhaps interacts with one constituent of the other proton, and they go through some sort of what's called a hard collision. They do some things. You can calculate this hard scattering between the two, and a load of products are created as a result. So which they all turn into quarks, but all of these quarks interact, and there's some sort of long distance physics which turns them into particles that can be detected.
So presumably, the kind of classical thing, right, is that you're imagining that these, on the timescales you're dealing with, all of these parts of the proton are not interacting with one another.
Exactly.
And then you're saying that there's also a billiard ball kind of interaction with the other proton. So you're not treating that interaction between one part of the proton and another part of the other proton as quantum mechanical?
No, not at this stage. Yeah. So at the moment of collision, we treat it essentially as like classical. So when we compute at what's called tree level in quantum field theory, but you can add some quantum corrections to this hard scattering as well. So you can add quantum effects on top of that. But this is kind of at this point we've got kind of a handle on what's been ejected from the proton and what's interacting with another ejection from the other proton. Though there is another quantum aspect to it though. So this you can imagine as basically a purely classical interaction. So this kind of hard scattering interaction is what it's called. The quantum aspect is that we don't really know what's going to be ejected. Okay, there is this inherent like the quantum soupiness to do with the proton that we don't really know how much there is of everything at any given time. And these are the things that we parameterize the proton in terms of the functions that we use to tell us how much there is of each constituent are called parton distribution functions, and they basically capture all of the quantum weirdness that we can't describe nicely using quantum field theory, mainly because of these effects are they're very strong interactions. We can't really write down nice expansions, and we can't make predictions very easily with these things. These functions are unknown functions which tell us like roughly how much there is of each constituent at a given time. Specifically, though, these functions actually depend on the momentum of the the momentum of the constituents, and also the energy of the proton. So they've got a couple of like functional dependence. So they're functions of two variables, they're essentially like probability densities, if you like, as well. So they're telling you, like, what is the probability I'm going to get a gluon coming out and being the thing that participates if the proton is going at the specific energy, and what is the probability that I'm going to get an up being ejected, and that being the thing that participates.
So as you change as you dial up the energy, the probability that you'll see, I don't know, some muon being ejected is going to go up or down or something like that.
Yeah, that's exactly the kind of thing that you expect. Yeah, so like as the energy changes, you can get different things coming out. There's also another kind of probability aspect, which is how much of the momentum is going to be carried by that constituent. When the up is ejected, it might carry a bit more momentum, and the remaining fragment carries the rest of the momentum that it initially had. And depending on how much it gives, it changes the resulting products. So there's also this kind of probabilistic aspect, which also is described by these functions too as well. So these are kind of these unknown functions basically tell you all the things you don't know about the interaction. So the stuff that you can't describe in terms of these billiard balls. So the inherent like quantumness of the situation is packaged into these unknown functions that we say we are ignorant of. We can't really calculate them. So we've got to somehow get access to them. And the way that we do it is using experimental data. We try and infer them from the experiments. And
so you said these are experiments happening in the LHC. Do you get all of your data from the LHC, or do you get it from elsewhere as well?
We've got data from other experiments as well that goes into these kind of determinations of these functions. So the LHC is clearly like it's the main collider that's operating at the moment, along with the Tevatron. So the LHC is important in terms of a lot of the data that we get, but a lot of the data is also legacy data from old experiments, from like experiments in the 80s and the 90s and things like that. So from colliders that collided electrons and protons together, and these can be a bit more useful actually in the determination of proton structure, because there's only one proton in this, and the electron is fundamental. So the electron doesn't have this kind of like this quantum. There are quantum effects, but it's not got this issue.
You're taking out a huge number of variables.
Exactly. It makes things a lot easier to probe the structure of the proton.
Sure.
But it's from experiments that were done at like DESY in Germany. So things like the Hera experiments or the Zeus experiments. So yeah. But these are mostly like legacy data. But yeah.
I don't want to like jump the gun or anything, but my understanding is that in order to get as accurate a picture as possible and be able to say anything definitively, you can't just collide, 20 protons together. You have to collide like 20 trillion, I don't know, like a lot, before you can say anything.
Yeah, this is absolutely true. Yeah. So it's you because of the probabilistic nature of these things, you really do need to like high statistics in order to actually infer anything useful.
What are the sort of like quantities of collisions that we would be talking about in order to be able to, have enough statistical power to say something?
Oh goodness me! I don't know exactly.
Sorry, that's really putting you on the spot there.
Yeah,
Sorry,
no, it's quite all right. I feel like I want to say like 10 to the 8 collisions or something, like the number of collisions that the LHC has done like to date or something. I don't know. But that's possibly wrong. It's possibly wrong by like orders of magnitude. But the number is is the number that's come to mind, isn't it? Yeah. But yeah, so it's quite a lot. It's quite a lot.
Could you say that's like 0.1 of a giga collision?
Yeah, I guess.
Giga 10 to the 9.
I think so.
Like
yeah. Possibly. Yeah. You can tell that I'm mostly a theorist, and that I have no idea what the numbers are. But yeah.
Can I ask then? Have there been? So obviously, the most famous discovery from the LHC is the Higgs, and was that does this parton model have some part to play in that discovery?
Yes, yeah,
definitely. In other discoveries?
It definitely does. So yeah, so like whenever you collide protons together, then this is important. So having an understanding of these functions is important. So understanding proton structure is absolutely essential in making any predictions, basically, for the LHC. So of course, it's only one ingredient of essential predictions that you need. Obviously, you need to understand this hard cross section as well, so the billiard ball interactions, and that's something else that people do. They do very, very high order calculations involving this kind of like this hard scattering. Also involving quantum corrections there as well, so it's not purely classical actually. So it's a bit of a so that's another key aspect as well. People look at like hadronization as well, which is the sort of thing that you get at the detector, because quarks are not the things that you get at the detector in the end. Lots of stuff happens after the billiard ball interaction. You get this effect called parton showering. So there's loads and loads of different ingredients that go in.
Okay, sounds very complicated.
Yeah.
Hadronization then is what exactly is that? Like it's sort of quarks becoming hadrons in some way? That's
the idea, yeah. So quarks have this property that they're called confined, okay, in that you cannot see a quark on its own. So it's impossible to see a quark on its own. It must be a constituent of a hadron. So it must be part of a composite particle. And that means that if the parton model was literally true, there would be difficulties, because you would have a quark interacting with a quark, and then like two quarks come out the other ends. You should see the quarks. So something has to happen to the quarks. That procedure is a kind of two-phase procedure. One is called like parton showering, so where the quarks undergo loads of virtual interactions, and the end result is something called hadronization of the quarks, and you get composite particles out at the end. But this is all, this is another highly complicated thing that people model and try to understand well. But this is distinct from the proton structure, I guess. Yeah. So
just so I know that we've covered all our bases. So a hadron is, just for some definitions, a hadron is any combination of quarks, right?
That's right. It's a composite particle. Exactly.
And if you were to try, if a listener has never heard of a quark before, what would you say, like, and they have no idea what we're talking about? They may well have stopped listening by now, but
apologies if that's the case.
No. What's the, like, how should we think of these things? Like, why do we need quarks in order to describe, nature?
That's a good question. So I mean, quarks. The fact that you can't see them means that it's you might assume that it's quite difficult as a result to deduce the existence of quarks.
Yeah, it seems like there's some philosophical problem here.
Yeah. Like if we've never seen a quark, so therefore like why should we believe that they exist? So there's like varieties of evidence, to be honest. Like starting in like the 50s and 60s, which all combine together to imply the indirect existence of quarks. One of the most convincing things is actually like the distribution of baryon structure. So baryons are combinations of three quarks, but people didn't know that at the time. They just saw these particles, and they categorized them using properties that these things have, and put them in like nice diagrams and stuck them all together. But they realized that if you want to describe these particles quantumly, there is no consistent way of doing it without there being some additional hidden degree of freedom that must be hidden hidden behind these particles. And people initially said, well, we're going to just chuck this extra degree of freedom in, just to make all the calculations work. But other pieces of evidence basically suggested over time that, really the thing behind this was this kind of this quark structure inside the baryons. So this kind of this distribution of baryon structure, the combination with the first experiments involving proton collisions, where the parton model was found to be really a really good description. At the time the parton model was introduced, the quarks were not necessarily the thing that was inside the proton, but any old constituent was just chucked in as the thing that you could describe it with. In fact, if you try and come up with a composite model of the proton that doesn't use quarks, it uses a different type of particle, then you'll find that it disagrees with experimental evidence. So this is another good evidence for the existence of these things inside the protons. So there's lots of evidence that kind of points to the existence of these things, this more fundamental particle inside protons, and inside general composite particles.
And when you say there's a degree of freedom that you need in order to describe experimental evidence, are you talking there about the flavor of quark, up, down, strains, etc., or are you talking about color?
Specific color is the thing that we're missing. So,
are you able to describe color a little bit for the listener?
Yeah. So the theory that quarks fit into is a theory called quantum chromodynamics, which is like quantum electrodynamics, which is the theory that involves electric charges and how this interact, how photons and electrons interact. But it upgrades the idea of charge to being actually a combination of three colors instead, which are called red, green, and blue. So quarks carry this extra thing called color charge, but it's really a combination of colors. So it's a mix of colors that they also have. And it turns out that this is the correct theory to add this extra degree of freedom that describes the baryon structure correctly. This idea of having this thing, this color, the color on top. It's not actually literal color, of course, so it's not like it's not exactly like the quarks are actually colored red. It's just the fact that there were three things that were needed to describe it. It's a space of three things and combinations of these three. And people were like, what are three things? Oh, three colors, let's just call it these three colors instead. So it's not exactly like it was.
That's not going to get confusing at all.
No. People didn't think about this at the time, but
Sometimes I think physicists just grab the first metaphor or term that's useful for describing what the maths is saying, and then they just stick with it.
Basically, probably a million other things would have been better to call it, but we're stuck with it now.
Fair enough. Okay, cool. So we've sort of got an idea of the structure of the proton, why we have evidence for believing that is in fact the structure. But you mentioned that you're also looking for extra physics hidden in that structure somewhere. Are you able to sort of describe that a little bit?
Yeah, that's true. So that's the main thing that I work on here in Cambridge, and the group here works on in Cambridge. So when people normally kind of determine these functions which describe proton structure, the parton distributions, when they're normally extracted from data, they're normally extracted from data under the assumption of the standard model. So you normally say, here's my data, here's my theory which involves these functions, I compare the two of them, and I extract the functions. Okay, that's broad brushstrokes kind of what you do. But of course, when you do that, you have to choose what theory you're going to be using. So, and the theory that people use is the standard model. And people say, we'll extract these functions, and as a result, you get some functions which work well, assuming that the standard model is correct. Okay. Mm-hmm. You might reasonably say, well, what if the standard model is not correct? What if there are things beyond the standard model that could help better explain the data? What if we added extra degrees of freedom to our model? Would we get better fits to the data in that case? And that's kind of the basic philosophy that we work with here in Cambridge. It's kind of the idea is, I don't know, an example of things that I've worked on is like dark matter constituents inside the proton. Mm-hmm. So one thing that you could add to proton structure is something called a dark photon. You could say, what if there was this additional photon inside the proton? There is, of course, a photon already there because we know that photons exist. But what if there was this extra dark photon? So this hypothetical particle, which might be an example of something like dark matter. What if we added that? And the idea, you could then say, you go through the logical conclusions of adding that particle. You could make predictions using that theory, compare to the data, and try to extract the functions. And if the functions that you get fit the data better, you might reasonably say that, okay, there might be some evidence here to suggest the existence of this dark photon instead. So it's kind of a possible avenue for like discovery of new particles, indirect discovery of new particles.
So just talking about bad terminology, the surely dark photon is the worst named particle.
Possibly, yeah. It's a pretty bad name, yeah. So I mean,
oxymoronic.
Perhaps, yeah. So it's invisible as well. I don't know, yeah. So you can't see it, anyway, yeah. So, but yeah, it's a pretty bad name, yeah. But I guess fair. The name is given mainly because of the kind of the interactions it would have would be similar to a photon, but they would be interacting with kind of a dark sector in kind of the same way, and in kind of like a mirror universe type thing, but they would all be dark particles, and somehow they would interact a bit with the standard model particles. So you might be able to see them a little bit, but not very much. But anyway.
Fair enough.
Though it's worth saying that actually I've singled out a specific particle here and said, what if there is a dark photon inside the proton? This is not strictly what we do most of the time here in Cambridge. Most of the time, what we do is we try to go with more kind of model independent approaches. So we don't say, let's just guess a particle and see if it exists. Just pick, because obviously, this is not a sustainable approach. What we tend to do instead is work with what are called effective field theories, which are supposed to parameterize like deviations from the standard model in all the possible directions you could go, and they do them in an effective field theory is a tool which organizes how important these deviations would be. So you can say, here are all the deviations that would show up first, and here are all the deviations which would show up at sub-leading level, and here are all the other deviations, etc., etc. And you can then fit all of the parameters in this kind of like this effective field theory framework alongside your proton structure functions. And if you get a signal that one of the deviations is important, you can say, there is something beyond the standard model that generates this kind of like this weird interaction between standard model particles we weren't expecting. That must reveal some sort of new physics that we don't know about, basically. So this is the idea of an effective field theory framework, and that's kind of more generally what we do, because we don't really want to just pin our hopes on just random models. So we try to be a bit more agnostic. But yeah.
Interesting. So these deviations that you're dealing with in effective field theory, those are not the same as new particles necessarily. They could be sort of somehow combinations of new particles or something like that.
Exactly, yeah. So anything. So the idea is that in this kind of this effective field theory that we work with, any of the deviations we see they would have to be generated by some unknown theory. And the point is, at the energy scales that we have currently access to, the unknown theory, the way it manifests is via interactions of the existing standard model particles. So the way that you see it is via these kind of like interactions you weren't expecting between the standard model particles. A great example of this is actually in the 70s and the 80s. Actually, people didn't know about the existence of the W boson. Okay, and not knowing the existence of the W boson means that you can't have certain interactions between muons, neutrinos, and a couple of the other fermions. So it looks like if you don't know about the existence of the W boson, you go to an experiment. You can do an experiment and you can see that, actually it looks like there's some weird interaction between 4 standard model particles that I wasn't expecting. So because I don't know about the existence of the W boson, so you can say you can write down a list of all the possible interactions you're not expecting and say, if I see any of these ones, then it must be the consequence of some new physics that I'm unaware of. And it turned out that later on people discovered the existence of the W boson, which explained this.
That's super interesting.
So yeah, effective field theory can be very nice. Yeah.
For those of us who continue to not know of the existence of the W boson, can you describe what it is and why the standard model needs it?
Yeah. So the W boson is one of the force carrying particles in the standard model. So it carries what's called the weak force along with the Z boson. It was discovered, I think, in the 70s and 80s, and it's important in what are called weak decays. It describes things like the beta decay is something that perhaps people have heard of in terms of like radioactivity. gravity inside of nuclei. This particle explains how that occurs, basically. So is the idea. But it's worth saying that, like, whilst we call it the weak force, like it's incredibly weak compared to the other forces that exist in terms of the standard model, but it's not as weak as gravity, which is really the weakest force. But because it is important enough that we can see effects of it in collider experiments. But
when people were seeing these signatures of interactions that they knew couldn't happen given the particles that they knew existed, what was their sort of explanation before the W boson was independently discovered? Or did they just say, well, the data is incorrect?
Unfortunately, the understanding of the corresponding mathematics at the time was not quite as good as our understanding now. One of the problems is like the interactions that they saw. These interactions between muons, neutrinos, and quarks. This interaction that they saw was like they were like, oh, it's just another interaction we're missing from the model. We'll just add it in. And you just chuck it in the model and say, oh, it's fine. Now we've got this other interaction. But it turns out that some types of interactions are actually banned from the standard model. They are what are called non-renormalizable interactions, and they're such that if you try and include your quantum corrections, you will find that you cannot include quantum corrections consistently in terms of the theory framework. These kind of interactions do not work out. It's impossible for them to be like fundamental descriptions of nature. There has to be something behind them. The maths doesn't work out at all. And if we believe the maths of particle physics, quantum field theory to be correct, then this cannot be an allowed interaction. But it can be something that you might see in an experiment and say, there is actually we can say that this thing is a signal for this interaction, but therefore that reveals that there must be some deeper new physics that we don't know about. And this is kind of a good direction to pursue, is come up with models that might describe the interaction.
Was what happened the case that they saw these interactions between particles? They wrote down a theory which included these sort of direct interactions between the various particles.
Yep.
And then later people said, oh, wait, hang on a sec. These interactions that you've written down are non-renormalizable. The whole theory breaks, or did they sort of know that there were issues?
I think the sequence was that people discovered these interactions and were like, oh, we'll add this in. This gives us a good description of weak decays. Now we have a complete theory of that. And then people discovered the W boson and they were like, oh, well, actually that explains it a bit better. So let's chuck that in instead and get rid of these interactions. And then people discovered that actually these kind of interactions are not. You could have actually known a little bit earlier on that was something.
Yeah.
In the kind of like the 80s, people realized that in the late 80s, people were like, oh, actually we could have realized this a bit earlier on, that that there was something beyond the theory that we currently have. And that's something that is now taken to heart in terms of like most new physics searchers. People now strongly taking into account this effective field theory framework. And say that this is the best way to hunt for new physics. But yeah.
Maybe you just want to give us the sort of 30-second pitch of quantum field theory and how it relates to particle physics.
Sure. So
if that's okay, I'm asking a lot of you today, James.
No, it's quite all right.
I think you can handle it.
Yeah. So it's fine. It's fine. Okay. So quantum field theory is kind of our best description of nature as it stands today, and it stems from what are called where it stems from field theory. It's a quantum version of field theory, so it's a good name for something in physics, which is unusual. So what is a field theory? First of all, well, it's a theory where the fundamental things, the fundamental objects are fields instead of particles. So instead of like little billiard balls in kind of like Newtonian physics, the standard description from the 1600s, the fundamental degrees of freedom are these things that fill space and time. And they're more like basically like big blocks of jelly, if you like, that can wobble around, move around in the middle. So this is what a field really is. And you might be familiar with the ideas of like the electric field or the magnetic field, something that fills all of space, and you can propagate waves through it by oscillating the field at different points. The revolutionary idea of quantum field theory is that all of the particles that we previously thought about, so things like the electron, so things like the proton, well, not the proton, but the constituents of the proton, all of these things also have their own field. So they also there is an electron jelly that also fills the universe, and oscillations in the electron jelly can cause oscillations in the photon jelly, and and corresponding with one another. They interact in different ways. So how does the picture of so this is what quantum field theory is. Quantum field theory is kind of like the idea of having this field theory, but then quantizing it, so adding quantum effects on top of this. So and it's worth saying though, I've just said, oh, everything's now a field. The electron is actually a field that fills the universe, and there's really an electron field. But I've been talking about particles the entire time. So what really is a particle? Well, a particle is kind of like a small excitation of the field. Like something that it's not a billiard ball anymore, but it's kind of a local excitation. So it's a small excitation that maybe we can detect. So on large scales, it kind of looks like a particle. But so is the general idea, and we treat it in kind of like when we actually do quantum field theory, we treat things as like point-like excitations. So like infinite excitations in a small point to a good approximation. This is how we might describe it. So
Well, thanks for that. Just jumping back, just absolute whiplash here, but to go back to the non-renormalizable interactions that you were just talking about.
Yeah.
This might be a really naive question, but when you're doing your effective field theory calculations, you're writing down these interactions that could describe some sort of more fundamental physics or something on top of the standard model and seeing if they fit the data. Are you including non-renormalizable interactions in those possible things that you write down?
That's exactly the idea. So so we include these non-renormalizable ones, which we know are banned by the theory. We're not allowed to use them, but we add them on anyway because we say, okay, if we add one of these things and we add it to our theory and try and measure the effect of it, then if we get a contribution from it that's important in the data, it describes the data better, then it means that this operator is actually useful in the theory. There must be some way of replacing it with more fundamental new physics later on. So that we must be able to get rid of it eventually. The point is that we now have a better understanding of these non-renormalizable interactions in the idea that we think that they're only valid to consider as interactions up to a specific energy scale, beyond which you have to get rid of them and they won't work after that. So and this was fine when people were looking at like the W boson discovery in the sense that they were only working with very low energy experiments, and they were saying the theory is working perfectly fine, but it couldn't be the fundamental theory because actually these operators will break down at some point. These contributions don't work anymore. So at the level of the LHC now, we're working at like 13 tera electron volts is the amount that protons are collided at, and this is okay for us because we can now say that's the energy scale beyond which we have no guarantee our theory is going to work after that. There's going to be some point at which we expect it to break down, but we don't know where that point is. And it's okay to use these effective field theory kind of like contributions that are non-renormalizable, as long as we promise later on that we're going to fix it.
So punk rock.
It's sort of like you're building a car which is going to fall apart if you go past 70 miles an hour.
Basically, yeah. So it's like guarantee, like a safety notice on the car, exactly, saying do not exceed, this speed. Basically.
Yeah, that's really fascinating. And because people were very skeptical about this whole renormalization thing for a long time, right? I think it was Dirac who I think was really thought this was all absolute rubbish.
Yeah, I think Feynman also he was very unhappy with it as well. I think I don't know.
Right.
I can't remember specifically who. There's someone called it dippy nonsense at some point. I think, which was I think there was I don't know, but people really kind of changed their view of renormalization. I think, and the idea in the 80s when people started kind of viewing it in this effective field theory framework instead. One of the problems is that it first appeared in quantum field theory in the 40s. Actually, when quantum field theory was first being developed, and people tried to look at these kind of interactions, and they realized that if they tried to make predictions with them, they got loads of infinities as their answers, and they were predicting that the electron mass should be infinite actually or something, and which is clearly nonsense. But people started to understand how to deal with these infinities properly in a sensible way later in the century, and the problems that quantum field theory was plagued with initially were fixed basically over time. So people started to understand why they happened. So,
right.
At least to the satisfaction of physicists, not necessarily to the satisfaction of mathematicians, but that's another story. So yeah.
So I promise that we'll get to the question about errors very soon. But just I feel like tie a bow on this part of the discussion, the effective part of effective field theory how does that come in? Like, why is that different to just sort of regular old quantum field theory?
So the effective refers to the fact that it's only valid below a certain scale. So it's an effective theory that it only works in this kind of like regime. So cool. But really the actual description is more complicated and it's like hidden and we don't understand it. But we can use this as an effective placeholder, if you like, before we get to the actual theory. So
right. So it's the car that falls apart.
Exactly.
You get too fast. Yeah. So another example of an effective theory could be something like the fluid model of water or something like that, right?
Yeah, that's the sort of thing that we're thinking about. So effective field theories, like effective theories in general occur all sorts of times and in all sorts of places in physics. And maybe a great example is that modeling gravity is just something that pulls go straight down. Like imagining that the Earth is flat, and like when you chuck balls up, they just come straight down, and gravity works at whatever it is, 9.8 meters per second squared or something. I don't know. So that's an effective theory of gravity when you are kind of at the human scales on the surface of the Earth. But when you're working with the planets, you need to like treat gravity as like this inverse square law instead. Like it's not really like 9.8 meters per second and it points straight down anymore. It's really much more complicated. So yeah, but when you think about it at these small scales, this is a good enough theory that works.
Sure. And then I guess Newton's theory of gravity, the inverse square law and all of that itself is an effective theory of general relativity. Exactly.
Yeah. So if you look at appropriate limits of general relativity, you can recover Newtonian gravity. Yeah.
Cool. Okay. Well, before we move on, Brian, do you have any further questions about what we've talked about so far?
This idea of you're trying to carve out, look at these interactions that still need some kind of description or updated explanation. Like, do you have a specific example of something that you're seeing and it's like, we're not sure yet, so let's take a look? Is there like a specific case of that you can talk about?
Unfortunately not. So everything that we get with all our fits is fully consistent with the standard model. So so we find that that all of the interactions that we propose, these non-renormalizable interactions in the effective field theory, they're all perfectly consistent with the standard model, them being zero basically. So as far as we can tell with the current data that we have and all of the scenarios that we've thought about so far, the standard model works perfectly fine, which is disappointing, but there we are. It's just telling you it works great, and we've not seen any new physics just yet. But it's certainly possible that in the future you might see some more deviations as we get to higher and higher energies and things get
right.
Yeah.
Are there not examples, potentially not to full significance yet, but to, I don't know, something like 3 sigma, which could be sort of beyond the Stand model signatures?
Not quite. So in terms of the biggest deviation that we've seen is 2 sigma deviations actually. The vast majority of the time we see 1 sigma deviations. But you're right that in particle physics you expect a 5 sigma deviation before you can claim that anything is actually successful.
What I was thinking of was it's like the magnetic moment of the muon or something like that, isn't that
That's true. So there are indications that there is physics beyond the standard model, but not in our effective field theory approaches. So in terms of any effective field theory we always get nice consistent results with the standard model. But certainly there are experimental there has been experimental evidence that there is some sort of deviation from the standard model. One example is the magnetic dipole moment of the muon, which is measured to be inconsistent with standard model predictions by about 3 sigma. And though that also depends on what predictions you use. There are lots of ways that you could obtain theory predictions for these experiments. One way is using the kind of like the perturbative quantum field theory framework that we use. Another alternative is to use what's called lattice field theory, where you can also get results for this. They're actually a lot closer to the results that you get for the magnetic dipole moment moment of the muon. So that kind of is not necessarily like something that is pointing to anything. There are other things though. There's things like what are called B anomalies, which they are also in slight conflict with the standard model. They are to do with like ratios of B meson decays to muons and to electrons, which should be the same in the standard model, but are not observed to be the same, 2-3 sigma. That is some of them are explained and have been updated due to like poor measurement, but and some of them still exist, but not so much anymore. And another great example that has happened recently actually is the W boson mass itself, actually. So we've been talking about the W boson. This is a possible indication of new physics. There was a W boson measurement by the Tevatron, in America, which was in, I think, 7 sigma conflict with the other measured values of the W boson. This measurement has been like highly questioned though, and the theory predictions that have gone into it also highly questioned, and people are not too terribly satisfied with it. So it can be quite contentious, to be honest. Like claiming new physics obviously is like a big thing. So
Can I just suggest we've been talking for a little while already. Maybe we hit pause on this conversation and leave the rest for next week's episode. Yeah. What do you think, Brian?
Sounds good to me.
Okay.
Sure. So, as always, thank you everybody for listening to Question Field. Especially thank you to Andrew for your question, which we will get to, we promise. And a big thank to James for joining us and talking to us. Thank you.
You're very welcome. Yeah, thanks for having me.
You've been listening to Question Field. Question Field is a Gain Media production and is produced by its hosts Campbell McLaughlin and Brian Buchanan. For more information, please check us out on Instagram at QuestionFieldPod, on Twitter at QuestFieldPod, and on TikTok at QuestionField. If you have a question you'd like to submit, or would simply like to leave a message, please send us an email at questionfieldpod@gmail.com. Recently, the James Webb Telescope discovered 5 new stars located in the review section of your favorite podcast app. Thank you for listening.